All right, so the plan for today is just to finish up the last little bit of correlation and regression. We got through most of it last time, but just a few extra little tidbits to get through. I'm going to put an Excel file in chat that we'll be using. So I just did that. And then we'll start on chi-square tests. So the last of these couple of assorted topics that we're covering at the end of the course. So finishing up correlation regression, we'll start chi-square tests, and then this coming Monday, we do have a regularly scheduled class meeting. The final exam week runs Tuesday through the following Monday, so we have class on Monday the 6th, and there we'll finish up chi-square tests of goodness of fit and independence, and we'll discuss ANOVA, the analysis of variance. On the 8th, there will be an optional review session from 10:30 to 12:30. Again, I'll just treat that basically like office hours, and I'll use the same Zoom link as normal class. So if you want to pop in and ask any questions or anything, feel free to. The final exam will be available from the 3rd through the 10th, so this Friday through the following Friday. So we're coming up on it pretty quickly here. It's the same setup as the midterm exam, taken on MyStatLab using Examity. The formula sheets and probability distribution tables that you can use are uploaded on Blackboard. So I would recommend downloading those. You can either download them and print them off if you want a physical copy, or you can download them and keep them as a PDF on your computer and use it that way, or you could do both. You can have, a physical copy and a PDF, so you have it in a couple of different formats, whatever works best for you. And I guess I didn't say it on here, but yesterday I uploaded some supplemental videos for the material that we're going to cover on chi-squared and ANOVA. So that way, since we're only technically covering that material next Monday, if you wanted to take the final exam a bit early, you can watch those videos, and they're just going through the exact same material we'll cover in class. So if you want to, you can watch those videos and you can take the exam early, or if you want to, you can come to Monday's class if you're planning to take the exam next week. I do strongly recommend that you take the exam, I would say Wednesday at the latest. Plan to take the exam Wednesday at the latest. And that way, if you do go to take the exam and something comes up, if there's a tech glitch, if there's a power outage, an internet problem, whatever it may be, that gives you time to get any of that worked out before the due date, Friday the 10th at 11:59 p.m. There are no due date extensions. I need to get the exams for all of my classes graded, final grades compiled and entered pretty quickly, so that students can plan their summer semester or get things sent off to their for transfer or anything like that they need. Okay, are there any questions on anything before we get started? All right, so then let's work on finishing correlation and regression. So just give me a second to get things set up here. Oh, and the quotes of the day for today. I have 3 quotes of the day for today, so we won't do one on Monday because I have this class on algebra tomorrow, and then that's their last class. So 2 quotes from Norm Macdonald, which I think kind of go together and I think are interesting thoughts, especially from a guy who's like a goofball comedian. If you've ever seen any of Norm Macdonald's stuff, he's kind of like, one of those goofy comedians, but that does seem to be his character, maybe not him personally. So there was a tweet that he sent out in 2018 where he said, and he passed away a few years ago, unfortunately, but tweet in 2018 where he says, the idiot sees the world as good versus evil. The cynic sees the world as evil versus evil. And the truth that no one seems to be able to see is that the world is and always has been a battle of good versus good. Right? Usually people who are fighting aren't fighting because they know that they're the bad guy, but they're just annoyed or something like that. Usually when you have two sides fighting or two sides arguing, both somehow think they're in the right. So it might be a bit naive to see the world as good versus evil in that sense. It's trying to recognize that there are other points of view in the world. And kind of on that note, in one of his interviews, I think this was in one of the late night shows or somewhere where they were interviewing him, or maybe it was like a stand-up routine on a late night show. He says, it says here in this history book that luckily the good guys have won every time. What are the odds, right? So as they say, the winners write the history, and so always something to keep in mind. And then lastly, a quote from my buddy who's in finance. He lives in St. Louis, name's Mark. And I just really like this quote from him. I think it's a good life lesson kind of idea, where he says, 10 times out of 10, I take a questionable contract with a solid person over an ironclad contract with a questionable person. So especially somebody working in finance, dealing with a lot of contracts, he's had a lot of experience with that. And, the person means more than the piece of paper. So that's something that, I don't know, I think it's just a good lesson. And, especially if you're looking for, say, a career or something like that, and you graduate, you're looking at jobs and you have a couple different job offers, or you're trying to decide, do I want to work with this company or not? Sometimes it might be worth it to sacrifice a few bucks or a little bit of a benefit or something like that to work with a company where it seems the culture is really, really solid. So, okay, so moving on to finish correlation and regression. I think I'm just going to minimize that so that we can get Excel on the screen a little bigger. All right, and just a last couple of ideas with regression here. And this is just to point out some things that we might want to keep an eye out for if we're running regressions. We've seen some kind of problems with regression, or maybe not problems, but some indicators that a regression model is maybe not such a great model. What are we looking for in a regression model? We're looking for a high R-squared, a high coefficient of determination, one that's near 1 and not near 0. And we're looking for a low p-value for the slope. We're looking for the ability to reject the null that the actual slope is just 0 in favor of the alternative that the slope is not 0. In other words, that there is a component of a linear relationship between the two variables. So here I've set up kind of a dummy problem where X and Y just have a scatter plot in this grid here. So 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3 for the first 9. And then there's a 10th point that's over here at 10, 10, way off to the top right. So how is correlation or regression affected by maybe 1 point out of 10? Well, the correlation of data points 1 through 9 is 0, right? If we look at this just square of 9 data points here, if we kind of imagine putting a crosshairs through the middle point, we'd have the same amount of data in each of the 4 quadrants. If we try to model this blob with a straight line, really any straight line, it's not going to do a particularly good job no matter which straight line we choose. It has correlation 0. And that's the actual correlation, right? It's literally 0. What if I add this 1 point in here, 10, 10? This point is kind of far off to the right. It has what sometimes is actually called leverage. It has a lot of leverage. It has a lot of an undue amount of influence on the problem because it's far off to the right, and it's kind of the only point that's far off to the right. In a fairly literal sense, it has like a lot of leverage on the problem. Like if you push on this point over here at 1010, it can kind of rotate the whole thing by quite a bit. If I compute the correlation of all 10 data points, it actually turns out to be positive 0.9. And that's really all due to this single data point over here. That's something we want to be careful of when we're evaluating correlations and regressions, right? Is if I get a correlation of 0.9, I always want to kind of look at the picture and ask myself, does that seem reasonable based on the picture, right? Is this something like the height and weight data that we, would kind of continually use as an example in class, where it's like you can see the data all kind of progressing bottom left to top right, more or less? Or does it seem like maybe we just have a blob of data and one or two highly influential points that are really overrepresented in that correlation number? And I think that's what we have here. And if we want to do a regression, again, Excel will essentially always give us a result if we tell it to run a regression. There are some very strange cases where it kind of blows up, but if we look at all 10, if we look at this data here, the regression line, if we plot a line through here, we see a positive correlation. We're guessing that we'll get a regression line with a positive slope. And that's what we get. We get a regression line with a positive slope. It has a p-value of 0.0003, or 0.03%, way under 1%. We would say this is a highly significant result. It has an R-squared of 82%. So 82% of the variation in Y is being explained by variations in X. But if I plot my line through here, my regression line, I mean, it doesn't look like it's doing a great job of modeling the data, considering that 90% of the data basically looks like this, just a blob. It's really just being influenced by this point out here at 10,10. Now, remember, one thing that I did note that we should qualitatively look at is the plot of the residuals, the plot of the errors. And we should ask, we had an assumption that said, well, our errors, the random variable that represents the error, should be normally distributed with a mean of 0 and a standard deviation that is constant. Well, if I look at this, and they should be independent. If I look at this picture here, and maybe it has a mean of 0. Okay, I see some above and some below. I don't know what I think about the standard deviation. It's a little hard to get a feeling for that, I think, with 10 data points. But I really don't think that this is independent, right? I see a definite pattern here. We start kind of high on the left, we progress down low, and then we have one point over here on the right. This definitely doesn't look independent. So that might give me a bit of pause. But these numbers here, the high R-squared and the low p-value, actually look really good. Even though if I were to plot the line on here, I would be hopefully pretty suspicious that that's not such a great model, because most of my data is just basically a blob. If I plot, or if I run a regression on the first 9, I see I get 0 for R-squared. I get 10 to the minus 17, or essentially 0 for the slope coefficient for X. I get a p-value of 100%, certainly not below 5% or 1%. Right, I get kind of a terrible result in a sense. This is like the worst regression you could get, right? 0 R-squared, p-value of basically 100%. It's so close to 100%, it just rounds it to 100%. And again, that's all due to the presence or absence of this one point here at 10, 10. So one point can have a huge influence on correlation or regression, especially if it has large leverage, if it's way off to the right or left relative to where all of the rest of the data is. That one point can have a huge influence. Something important to keep in mind with correlation regression. Another example of something that's, in this case, it's actually called a paradox, Simpson's paradox. Let me see if a picture can, there we go, can move up here a little bit. So something that's maybe paradoxical or something that we want to be aware of that can happen in regression is something like this. So again, this is kind of a dummy problem, but say that I have 8 data points. I have 4 of them that look like the bottom left here, 1, 4, 2, 3, 3, 2, 4, 1. Perfect linear relationship in the negative direction. Every time I increase 1 on X, I decrease 1 on Y. And on the top right, I have another 4 data points with a similar relationship. That's these 4, 10, 13, 11, 12, 12, 11, 13, 10. Again, every time I increase X by 1, I decrease Y by exactly 1. That's a perfect linear relationship in the negative direction. If I look at the correlation of the first 4 numbers, these bottom left, it's a -1 correlation, spot on, right? Because it's exactly a perfectly linear relationship. If I look at the correlation of the second 4, same thing. Perfect negative linear relationship. Its correlation is -1. But what's the correlation of all of them? If I consider all 8 data points together, I see that overall that's going to have a positive relationship. That overall, as I go left to right, values that are data points with an X value that's further to the right tend to have a Y value that's higher overall. Locally, as I increase X, Y decreases, but kind of globally, as I increase X, Y increases. I'm being a little bit imprecise here by saying increase, but you get the idea. The correlation of all of them is 0.88. So a very strongly positive relationship overall, but each of these 2 little pieces here has a strong negative correlation. So we might have, say, 2 different populations. Each population individually behaves in a negative correlation kind of manner. But when I combine those 2 populations together, they overall behave in a positive correlation type of manner. If I run a regression just on, say, the first 4 data points, I get an R-squared of 100%. I get a p-value that it doesn't even compute because it's just 0. It's a 65,000 standard error result, right? So it's a perfect line that goes through all 4 of these points. That's as good of a regression as I can get. If I compute a regression for all of them, though, all of my data points, all 8, I get an R-squared of about 0.8. So I'm explaining about 80% of the variation in Y by variations in X. I get a p-value of 0.3%, under 1%, so this would be a highly significant result. But it looks like I have these kind of 2 subpopulations where in each subpopulation, Y goes down as X goes up. But because if X goes up far enough, I hit the other population that jumps way up in Y, then overall it's looking like as X goes up, Y goes up. There's a famous, there's a couple of famous examples of this. One is in a journal article that was published that's out there. It was dealing with kidney stones, and basically looking at a couple different treatments for kidney stones. And what they looked at was, it's something along the lines of like, you could either have small kidney stones or large kidney stones, and you could either have intervention A or intervention B. And it was something like intervention A is worse than intervention B for small kidney stones. We see that in the data. Intervention A is worse than intervention B for large kidney stones. We see that in the data. But overall, intervention B is better than intervention A. And you say, like, how can that possibly work out that way? Well, really at the heart of this is the idea that A over B plus C over D is not equal to A plus C over B plus D. And that's really, this fact, dealing with fractions, is really kind of at the heart of this idea. There's another example that's pretty famous, the Berkeley gender bias case study, I suppose, where so the University of California at Berkeley, somebody scrutinized their admissions. They looked at their admissions and saw, okay, how many males versus females are you admitting to graduate programs? And what they found is they looked at all graduate applications and all graduate admissions, and they found that males were being admitted at a higher rate than females. And not just, a little bit higher, but like statistically significantly higher. So they said, okay, this seems problematic. Let's see which department has this, or department or departments have this bias, let's say. But they looked at each department, and as they looked at the departments, each department would tend to favor women. And so they said, wait, how can essentially all the departments favor women, but the overall result is that men are favored? And essentially, again, it comes back to this kind of idea with fractions here. Essentially, what it was is that it tended to be the case that the programs that men were applying for had higher acceptance rates for those programs. There were maybe more seats available relative to the number of applicants for the areas of interest that men tended to be interested in. So, typically things like STEM fields. And the areas of interest that women were interested in tended to be a little more competitive for those seats. So things maybe in the humanities, things like that. So again, it's, even though each program slightly maybe favored women over men, overall, the men were favored over the women because of that choice of program. So it's a similar idea to the kidney stones, where a larger or smaller kidney stone might influence the physician's choice of treatment. So as an aside on the Berkeley gender bias study, it's a famous example. It's almost a canonical example. There are claims that there was a lawsuit and that this came out in the lawsuit. There are claims that, there were just people concerned about this and they looked into it. It seems like, at least as far as I can tell, the evidence for exactly like how this came about is kind of uncertain and kind of murky. It's kind of strange in our, information age that we don't have like all of this information at our fingertips. I think there have been people who have really researched the legal side, and they said they can't find any actual evidence of a lawsuit against Berkeley for this. So it probably wasn't from a lawsuit, but it's one of these, examples that everybody uses. So it may be true, it may be not quite true, but you can think of it either, I don't know, it depends on how you define so whether something is true or not, right? But you can think of it just as a toy example if you want to, as a way that that something strange could happen, something paradoxical could happen. So this idea of Simpson's paradox, where we have different subpopulations where each subpopulation behaves one way, but the overall population, when those subpopulations are all combined together, behaves a completely different way. And again, I think this is why it's so important to, and I mentioned this a couple of times, to not just look at the numbers, not just say, oh, high R squared, low p-value, my regression is great, give it a thumbs up and move on. but to actually plot the regression line over the data and see if you think it's a good model. And in this case, if I plotted the regression line, I'd see a positive line going through these, but I would very clearly see these two subpopulations. And I might be a little suspicious of my model, depending on what I'm trying to say with my model. Okay, any questions on correlation and regression? Okay, so correlation and regression, that was kind of our last somewhat big topic, even though we only spent a couple of days on it. The other topics, chi-square goodness of fit, chi-squared independence test, and ANOVA, are kind of also, they're smaller topics. They're topics that I'm throwing in because these come up in applications quite a bit. So in the social sciences, in biology, and so on, you'll see these tests used. I took a genetics course a while ago, and we used actually a chi-square goodness of fit test. You'll see ANOVA used a lot in things like psychology and sociology. So I think it's important to go through and kind of discuss them and have a bit of a feel for what they are and how they work. We will go fairly thoroughly through the chi-square tests. We will just scratch the surface of ANOVA. But hopefully at the end of this, you'll have a little bit of an idea of how these all work, and you can take that to your other classes as needed. Okay, so let's move on to chi-square tests. And today we'll probably try to get through chi-square goodness of fit test and then leave chi-square test for independence and ANOVA for Monday. Get my notes switched over here. Okay, so let's recall this example that we did in chapter 8. So suppose we want to run a hypothesis test for P, the probability of rolling a 1 on a 6-sided die that we think is fair. We roll the die 100 times and we get 21 ones. Well, 21 ones is a bit higher than we'd expect. We might expect 16 or 17. 21's a little high. Can we conclude the die is unfair on the basis of getting 21 ones in 100 rolls? Let's actually run through this hypothesis test just to kind of, we've been in correlation and regression for a couple classes now, just to remind ourselves how hypothesis testing works. Okay, so my hypotheses. We have hypotheses about P, the probability of rolling a 1. I want to know, can I conclude the die is unfair? So can I conclude that P is not equal to 0.5? It could be unfair if heads, or if 1 is more likely to come up than it should, or if it's less likely. And I said 0.5. I was thinking of coin flip for some reason. 1/6 is what I want there. And P equals 1/6 would be my null. So I'm trying to make fair dice. So I suspect that P is probably 1/6, that I'm probably manufacturing fair dice. I put a lot of time and effort into the machinery and so on to make the dice fair. But I do want to do quality control. I do want to check every once in a while. And if I have some strong evidence that 1 does not come up 1/6 of the time, 1/6 of the time, then I'll reject the null in favor of the alternative, conclude that the die is unfair, and recalibrate my machinery as needed. So these are my hypotheses. I also have a sample of size 100. And in those 100 rolls, I got 21 ones. And remember, with hypothesis testing, we start by assuming H naught is true. So if H naught is true, what can I say then? I can say that my random variable p hat is normally distributed with a mean of, well, p under the null hypothesis is 1/6 and a standard deviation of, again, if H naught is true, p is 1/6, so my standard deviation is 1/6 times 5/6 pq over n under the radical. And let me bring up my calculator. We'll figure out what this is. I'll actually just switch my share to a full screen. So I need to do a square root of 1/6 times 5/6 over 100. And that's about 0.037. So here I have a normal distribution centered at 1/6. They're about 0.167. And I have a p hat observed, an observed probability of rolling a 1 of 21 over 100, 0.21. Okay, so if I were to reject the null in favor of the alternative for this sample for 21 heads, I'd also reject for, or I keep saying heads and tails, for 21 rolls of a 1. I'd reject for 22 or 23 or 24 ones. Anywhere further to the right would be more evidence against the null and in favor of the alternative. Remember, this is also a two-tail test. I would also reject if I had a very small number of x's, 10, 9, 8 ones that I had rolled in 100 rolls. I'd also think that that die is unfair if I rolled very few ones. So I also have kind of a mirror image tail over here. I can compute my p-value. So this is the probability that p hat, my random variable, is bigger than 0.21. And I need to double that for my two tails. Or this is twice the probability that z is bigger than, well, what's my z-score for 0.21? 0.21 minus the mean of 0.167 over the standard deviation, 0.037. So let's do that. So there's my numerator. And that gives me a 1.16. Or this is twice the probability that z is less than negative 1.16. We need a left tail to use our normal table. And probability z less than negative 1.16. I go to my negative 1.1 row and my 600ths column. And it looks like that is 0.1230. Or it looks like that's 24.6%. Now remember, my p-value tells me the probability that I would make a type 1 error if I rejected based on this sample. 24.6% of the time I would make a type 1 error. And we'll test at the 5% level. I didn't say that up here, but that's what we almost always use. So I'd say something like, since the p-value, I'm writing out p-value because we've got all kinds of other p's floating around in this problem. Since the p-value is 24.6%, this would be our actual error that we would encounter if we rejected. That is not less than 5%, which is alpha, our significance level. We do not reject. We do not reject H naught. We would not conclude the die is unfair on the basis of this sample. This couple of extra ones could easily have occurred just by sampling error. So what's another method we could use? We could use a rejection region method. Another method we could use is the critical value method. So alternatively, we could have used the critical value method. Geez, that's... just start over on that one. We can instead use the critical value method. This method's a little more abstract, but it kind of follows a similar pattern, except the critical value method is saying, let me find a z cutoff, a z critical, and let me find a z observed for this sample. And then I compare z observed to z critical. If z observed is farther in the tail in the correct direction than z critical, then I reject the null, otherwise I do not. So just like before, I assume H naught is true. And here I want to compute z observed, and I want to compute z critical. I think the p-value method is the more straightforward way, the more easily to understand way, but the critical value method generalizes a little nicer to some of these other tests. Okay, so what's z observed? What's the z-score for my observed sample under the null? Well, that's actually this number here. So z observed is my p hat observed minus my null hypothesized p hat over the standard error. My z observed is 1.16. I compute that using a formula. Z observed is p hat observed minus the null hypothesized value of p over, let's just call it something like sigma naught, the standard deviation using the null hypothesized values of p. My z critical, how do I compute z critical? Well, I have to remember this is a two-tail test. And alpha is 0.05, so I want to find the z index with half of 0.05 in each tail. So alpha is 0.05. I could look it up on my normal table. Let me hide zoom here. There we go. Could look it up on my normal table, but I could also go to my t table. I know that my t table kind of naturally gives me indices related to areas. It's a little more nicely set up for this kind of a problem. So I'm looking for a two-tail alpha, an area in two tails of 0.05. Now, these numbers up here are t distribution numbers, t indices for different degrees of freedom. But remember that the t distribution for infinitely many degrees of freedom is just the normal distribution. So this bottom line here is actually just normal distribution numbers. So I need area in two tails, the normal distribution value, all the way at the bottom, 1.96. And that's plus or minus. This is a two-tail test, so my decision criterion is if Z observed is bigger than 1.96 or Z observed is less than negative 1.96. If it's farther in the tail in either direction than that critical number, then we reject H naught. Otherwise, if Z observed is between negative 1.96 and positive 1.96, do not reject H naught. And we do notice that Z observed is 1.16. It is in between negative 1.96 and positive 1.96. It's not far enough into the tail to be out here in the right tail to the right of 1.96. So we do not reject H naught. We do not conclude the die is unfair. Now we might ask ourselves though, okay, I mean, we did this in chapter 8. So it was just a little bit of a recap of hypothesis testing. Never hurts to see that again. But we did that in chapter 8. But okay, we noticed that there was a shortcoming. This only looks at the ones, right? Maybe our die is unfair, but it's unfair in a way that like 6 comes up much more often than it should, and 5 comes up much less often than it should, but 1, 2, 3, 4 are about right. That would also be an unfair die. So you might say to yourself, okay, well, we'll just repeat the same test on the same die. We have 100 rolls. We recorded how many ones. We ran a test. We could just do the same test for the 2s and the 3, 4, 5, 6. We could just do the same test 6 times using the same sample and see if any of them come up with a rejection. That sounds like a pretty good idea, but it has a particular flaw. Remember our significance level of 5%. Well, what is that? What does their significance level of 5% mean? It means that when I decide on the basis of the number of ones that were rolled in my sample, whether to call a die unfair, I'm going to make it type 1 error 5% of the time. Alpha is my type 1 error rate. I'm going to call 5% of fair dice unfair just by chance, just by sampling error on the basis of the ones. That 5% is a number that I chose and that I'm maybe comfortable with. But the problem is that on the basis of the ones, I'll make a mistake 5% of the time. If I then run a test on the 2s, if I say, okay, if I get a rejection on the 2s, if I think that the 2s suggest the die is unfair, then I'm going to call the whole die unfair. Well, now I've got kind of another 5% error that I'm going to make. And for the 3s, another 5%. So my error starts to compound. Right? If I do one test for each of the numbers 1 through 6, and then say, if the die fails any of the tests, then I conclude it's unfair. All of a sudden, maybe I'm making something more along the lines of a 30% error rate, not a 5% error rate. That doesn't seem so appealing. So is there a way that I can kind of bake in from the very beginning that I can say, okay, I mean, I have this sample of 100 rolls. I have a certain number of ones rolled, a certain number of 2s, 3s, 4s, 5s, and 6s rolled that I observe. I also know what I would have expected to get, the number of 1s through 6s that I would have expected to get under a fair die. Is there a way to look at these all at the same time, all under one hypothesis test, and say whether my actual observed data overall is more or less in line with my actual expected data, whether any deviations could reasonably have occurred by sampling error, or whether the two were so far apart that I don't think it's just due to sampling error. So we don't want to just repeat the analysis 6 times. We want to consider a better approach. We want to consider all of the outcomes at the same time. Now, what's the idea here? Suppose that our die has this probability distribution, comes up 1 through 6 with probabilities P1 through P6. And we want to test this hypothesis. The null hypothesis is that's a fair die. In other words, P1 is 1/6, and P2 is 1/6, and so on. Or the alternative, that's an unfair die, that at least one of the PIs is not equal to 1/6. So let's say that we roll the die 120 times. I'm using 120 here just to make the numbers a little easier. If the null were true, if this is a fair die, we'd expect the sample to look like this, where we'd get 20 rolls of each. Now we know that even if it's a perfectly fair die, when we roll the die, there's going to be some sampling error. So if I got a couple 21s and a couple 19s, I wouldn't be suspicious at all. If I got a 25 and a 15, is that enough to be suspicious? If I got a 25 and a 30 and a 15 and a 10, is that far enough away to be suspicious? That's what we're trying to look at now. So suppose we do roll the die 120 times. If the die were perfectly fair and we got a perfectly representative sample, we'd expect this. But the sample that we actually obtained looks like this. It's not right in line with all 620s, but is it far enough away overall for us to conclude that this is unlikely to have happened by sampling error and this is evidence of an unfair die? Or is it close enough that it could reasonably have happened by sampling error? Okay, so what is the idea here? The idea that we're going to use here is that, so we're going to have O is the observed quantities. So we have like O1, O2, and so on through O6. That's a subscript 6. And E are the expected quantities. So we'll call this E1, E2 through E6. Now, the further away the observeds are from the expecteds, in general, the more suspicious that I am that this is an unfair die. So if I look at the observed minus the expecteds, their difference, the larger this number tends to be, the more suspicious that I am that the die is unfair. It would be really nice. So the observeds are from a sample. So this is a random variable, right? Under different rolls of the same die, I'm going to have different numbers of observeds. So this is a random variable. It would be really nice if I could know what its sampling distribution is, the way that I know that X bar under some criteria is roughly normally distributed. Well, observed minus expected doesn't quite work out nicely enough, but if we do observed minus expected over square root of expected, it turns out that this is approximately normal. So my random variable that looks like, say O1 minus E1 over square root of E1. Remember, O1 is a random variable. Under different repetitions of this experiment, I'm going to get different numbers of ones that I observe. So O1 is a random variable. E1 is just a fixed constant. So the variable O minus E over root E turns out to be approximately normal. if we square this to get observed minus expected squared, and then we have square root of expected squared on the bottom, or just expected on the bottom. So now I'm looking at the more or less the squared difference between, say, O1 and E1, or between O2 and E2, or between O3 and E3, and then I add them together. Or this looks like O1 minus E1 squared over E1 all the way out to O6 minus E6 squared over E6. Remember, the reason we would square this is I want to eventually get to the point where I add these together, right? So that I'm looking not just at the deviation of a single observed versus expected, but all of them overall. But if I add them together and some of them are positive and some of them are negative, it's just going to cancel out. So first I square, then add together. We've seen this trick several times in the past, but just to note that's what's going on here. But if observed minus expected over root expected is normal, then each of these terms here is like the square of a normal. So this is like a normal squared, and a bunch of those added together. And we had mentioned before that when we square standard normals and add them together, that's a chi-squared distribution. So now we have something interesting. We have kind of a chi-squared observed that takes into account all of the deviations between all of the observed versus the expecteds. It takes into account the whole distribution that we actually got versus the distribution that we would have expected to get if the null was true. So this is like a chi-squared observed. And then we can compare that to a chi-squared critical. Could this be a left tail test, a right tail test, or a two-tail test? Well, the higher chi-squared observed is, the larger in magnitude it is, the further in the tail, the more likely I am to generate a rejection. When do I get large chi-squared observeds? Well, I get large positive chi-squared observeds when the observed and the expecteds are far apart, right? When these numerators are large. When observed and expected are far apart, whenever the distribution that I observed really doesn't look anything like the one that I expected under the null, that's when I would get a large positive chi-squared observed, and that's when I would want to generate a rejection. This is always a right tail test. Again, if I ended up with a observed distribution that's very different than the expected one, the individual differences, the difference in the number of ones that I saw versus the number of ones I expected, and so on, those individual differences would be large, which would mean their squares are large, and when I scale them by the expecteds would still be large. Since I'm squaring them, they'll always be large positive, they'll never be large negative, there's always large positive. And when I add a bunch of large positives together, I get a large positive number. So when my observed distribution is way far away from my expected distribution, that's when I would want to reject the null. And that happens whenever I have a large chi-squared observed. So this is a right tail test. We do have an assumption. Again, this is one of those kind of rule of thumb assumptions. The assumption is that the expecteds are all at least 5. So up here where we have 20s in each of these boxes, we just need to make sure that those are all at least 5, that we're rolling the die, that our sample size is large enough that it makes all of these at least 5, and that is satisfied here, so that's fine. Okay. All right, so let's actually go through and compute our chi-squared observed for this. Let me actually copy these down so that we don't have to keep switching back and forth and make you seasick. So let's compute chi-squared observed. And remember, what it is the observed minus expected squared over expected. Do that for each of the different values. So we have observed 1, 26, minus expected 1 of 20, squared over expected number of 1s is 20. We have 25 minus 20 squared over 20. 9 minus 20 squared over 20. 19 minus 20 all squared over 20. 22 minus 20 squared over 20, and 19 minus 20 squared over 20. Or we see that the 1/20th can factor out. And for the first one, I have 6 squared or 36. The second one, 5 squared or 25. The third one is 11 squared, 121. The fourth one, 1 squared is just 1. The fifth, 2 squared, 4, and then 1. Or let's go to the calculator and figure this out. So that's 188 over 20, or 9.4. Right, so what is chi-squared critical? And here we'll use alpha equals 0.05. So if I ever just don't say an alpha, I'm just going to use 0.05. Let's bring up our chi-squared table. Now remember, this is a right tail test. So we're looking for a right tail area of 0.05. Remember that our chi-squared distribution looks kind of like this. And we're looking for chi-squared critical with 5% area to the right. Now we do need one more thing. We need to know which chi-square distribution are we on? What's the degrees of freedom? Degrees of freedom are n-1, just like we've seen before, or 6 minus 1, 5. So we need 5 degrees of freedom, area to the right of 5%. The area to the right of 5% is this column, and 5 degrees of freedom is this white row here. It looks like that is 11.071. So my chi-square critical is 11.071. my chi-squared observed is 9.4. Is my chi-squared observed large enough to reject the null? Are the two distributions far enough apart to give a large enough chi-squared observed that I can conclude that that sample, if the null was true, this sample would not likely have occurred just by sampling error? And the answer is no. I can say since chi-squared observed of 9.4 is not bigger than chi-squared critical of 11.071, we do not reject the null. We do not conclude that the die is unfair. And this might be a little surprising because we actually even had like a 9 here. That might have been pretty suspicious to us. And we had like a 25 and a 26, but our analysis showed that this could reasonably have happened by sampling error. So these two distributions overall are not far enough apart. The observed is not far enough away from what we would have expected under the null to conclude that the die overall is unfair. Okay, what if we had a different die? So here we have this set of observed. We got 7 1s, we got 0 6s, 38 2s. I think it's pretty clear that we're going to get a rejection here. Let's run the same analysis down here. So again, let's look at our chi-squared observed, but this time I think instead of doing it by hand, I'm going to use Excel, make things a little bit quicker. Okay, so what do I have? I have some expecteds and some observeds for my 6 possible results. So my expecteds are all 20. And my observeds are 7, 38, 30, 31, 14, and 0. Now remember, my chi-squared observed was the sum of the observed minus expected squared over the expecteds. So let me compute each one of these 6 terms separately here. So that's going to be, in parentheses, observed minus expected squared, that's the numerator, over expected. And I'll just double click in the bottom right hand corner to copy that down. Oops. And then to find our chi-squared observed, we just add these up. My chi-squared observed, it looks like, is 57.5. What's my chi-squared critical? It's actually the same that I found up here, isn't it? I still am going to use alpha equals 0.05, and I still have 5 degrees of freedom. My 6 data points minus 1. So my chi-squared critical was it 11.071? Yeah, 11.071. Remember, this is a right tail test. This is my chi-squared critical. And here I do see that my chi-squared observed at 57.5 is to the right of chi-squared critical. So here I can say since chi-squared observed at 57.5 is bigger than chi-squared critical, is bigger than 11.071, I do reject H naught, and I conclude this die is unfair. And again, for both of these tests, for this one and the previous example, I was looking at the die overall. I wasn't just looking at how many ones I got or how many fours I got or something. I was looking at the overall structure of the, maybe not structure, but in some sense, the overall frequency distributions. Okay, let's consider another example. What do we have? About a half an hour left. Trying to decide whether to do the next example or to leave it for Monday, but I think let's get started on the next example and then we'll see how far we get. We might cut this example a little bit short. Okay, so next example on Mendel's P experiments. This is one of the kind of famous uses of chi-square goodness of fit test. Not that Mendel originally did this, but when folks do these kind of, these types of studies or these types of experiments, in class or whatever, they tend to run chi-square goodness of fit tests, and that's one of the places you see it pop up in places like biology. So a little bit of background, Gregor Mendel, I think he was like a monk back in the, was it 1700s? It was a while ago. He was doing experiments with pea plants and some other plants too, but we'll focus on the pea plants, where he was trying to figure out basically how genetics works. I mean, they didn't call it genetics back then, but he was trying to figure out why it is that sometimes traits seem to be passed from generation to generation, and maybe some other times traits don't seem to be passed from generation to generation, trying to work out the details of how all that works. So he considered two characteristics of peas. One was color, yellow versus green, and the other was smoothness, smooth versus wrinkled. Our hypothesis here, and we'll say a little bit more about what we mean exactly here in a second, but our hypothesis is that the genetic inheritance pattern is Mendelian inheritance, with yellow and smooth as the dominant traits and green and wrinkled as recessive. Okay, so let's really quickly just say, what do we mean by dominant versus recessive? So each person, each dog or cat, or each pea plant gets one gene from mom and one gene from dad for, let's say chromosome 1 and chromosome 1. I don't know what chromosome yellow versus green or smooth and wrinkled peas are on, but you get one copy from mom, one copy from dad, and then you have two copies. So you could have inherited a gene from mom that says your color should be yellow. Or you could have inherited a gene from mom that says your color should be green. And likewise, you could have inherited from dad a gene that says yellow or green. So you could have these four options, right? You could have two yellow genes, a yellow from mom and a green from dad, a green from mom, a yellow from dad, or two green genes. If you have two genes that agree, I think it's pretty clear that your phenotype, your actual color, will be what they agree it should be. If you have two genes that disagree, if you have a yellow versus a green, well, who wins out? Do you turn out somewhere in the middle, or do you turn out yellow, or do you turn out green? And that's where the idea of dominant versus recessive inheritance is. And uh, the dominant is the one that wins out, because yellow is dominant, at least under our hypothesis. When there's a yellow against the green, the yellow wins out, and the color is yellow. Not everything turns out this way. Not every, you know, uh, not every characteristic or trait is Mendelian inherited. Not everyone is inherited in this dominant versus recessive way, but that's going to be our assumption here. So that's what we mean. The dominant trait, when there's kind of a battle between two different genes that disagree, the dominant is the one that wins out. The dominant is the one that you see as the phenotype or as the trait of the characteristic in the plant at the end. Now, of course, I mean, these days we can actually look at the genetic material and tell, if the color is yellow, we can tell if it's a yellow green or if it's yellow yellow genetically. But back, hundreds of years ago, Mendel was just crossing plants, and seeing what the characteristic turned out to be at the end. So we're going to perform what's called a dihybrid cross. We're going to take a plant that is genetically yellow-green and genetically smooth wrinkled. So it's going to look yellow and smooth, but it has this green and wrinkled kind of hiding in the background that are masked. And we're going to take another plant that has the same genotype, the same genetic makeup, and we're going to cross those together. And we're interested in figuring out what are the possibilities that we could end up with. So we're going to draw a Punnett square, as it's called. We could have drawn one over here for this simpler example, but it wasn't as difficult, so I just kind of wrote out all of the options that way. So plant one, what can it pass along? As far as yellow and green, it could pass along a yellow or a green. And as far as smooth or wrinkled, it could pass along smooth or wrinkled. So one possibility for plant one is that it passes along to its progeny, yellow smooth. Another possibility is that it passes along yellow wrinkled. We're going to kind of assume that more or less that these are on different chromosomes, or even if they're on the same chromosome, that they're at least kind of far apart on that chromosome. So they're not likely to be passed along together. So yellow smooth could pass along yellow wrinkled. We could pass along green smooth or green wrinkled from plant one. Those are plant one's four possibilities. When plant two decides, in a sense, which genes to pass on to its progeny, it also could pass along yellow smooth. It could pass along yellow wrinkled. It could pass along green smooth or green wrinkled. And in the middle here, we're going to say what the characteristic of the progeny is going to be, what it's going to look like. So anywhere that I see a yellow being passed along from either of the parents, this is plant 2, then the plant's going to look yellow. So this is going to be yellow, yellow. These ones have a green from plant 1, but they have a yellow from plant 2, so these are also going to be yellow. Similarly, for the second line, these are all going to be yellow. Even though these last two have a green from plant 1, they have a yellow from plant 2, so they're also going to look yellow. The left two columns both have a yellow from plant 1, so even though they have in these bottom 2 rows, even though they have a green from plant 2, they have a yellow from plant 1. That's dominant. It takes over. And then in the bottom right, the color is going to be green because we have a green from both parents. As far as smooth or wrinkled, smooth is dominant. So for instance, in column 1, the plant inherits a smooth from plant 1. So regardless of what it inherits from plant 2, it's going to be smooth. And the same thing with column 3. And the same thing with rows 1 and 3. And the only way that we're going to get a wrinkled plant for the progeny is if both parents, both ancestor plants 1 and 2, contribute wrinkled. So that would be here, 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 and here. So we have 4 different characteristic combinations for our progeny plant. It could be green wrinkled. It could be green smooth. I guess ironically, I didn't circle the green plants in green, but it could be yellow wrinkled. Or yellow smooth. So what do we see are the ratios of yellow smooth to yellow wrinkled to green smooth to green wrinkled under Mendelian inheritance in this manner. Well, we have 9 yellow smooths to 3 yellow wrinkleds to 3 green smooths to 1 green wrinkled. So they would be the ratios, or the proportions would be 9, 16, 9, 10, 11, 12, 13, 14, 15, 16, right? So 9 over the total of 16, 3 sixteenths, 3 sixteenths, and 1 16th. So if this was true, when I perform this experiment on a whole bunch of plants, I would expect that 9 sixteenths of the total number, roughly, would turn out to be yellow smooth. I would expect 3 sixteenths of them to be yellow wrinkled. I'd expect 3 sixteenths of them to be green smooth, and then 1 16th to be green wrinkled. So these are kind of my, from all the way up here, these are my null hypothesized PIs. So my null hypothesis is that probability of yellow smooth is 9 sixteenths. Let me say, and probability of yellow wrinkled is 3 sixteenths. And probability of green smooth is 3 sixteenths. and probability of green wrinkled is 1/16. And the null is basically not, or sorry, the alternative is basically not the null. That at least one of these probabilities is different than its null hypothesized value. Okay, I think we actually do have enough time to get through this. So are there any questions to this point? Oh, I see I missed some questions in chat. Okay, yeah, sorry, I missed a question in chat. I think a couple of folks were just confirming what I had said, but where did we get 11.071? Yeah, so sorry, since I'm in full screen mode, I didn't have chat up and didn't see that right away, but so 11.071, our chi-squared critical from the die example came from, we're using alpha equals 0.05, and this is a right tail test, so this is a one tail or right tail probability. And then our degrees of freedom are n-1, where n is the number of rows that we have. In some sense, the degrees of freedom is saying how many things am I free to choose however I want until I'm constrained for the remaining rows. I could choose these first 5 more or less however I want, as long as you leave me a 6 number to basically ensure that my, wherever it was up here, that my total number of rolls is 120. So the degrees of freedom is n-1, just like we've seen before, or 5. So this 11.071 comes from right tail area of 5% with 5 degrees of freedom. That's where that number comes from. Yep. All right, any other questions? Okay, so coming down here then. So this is our setup with this whole Mendelian inheritance business. And let's consider an experiment that gives the following observations. So we do this dihybrid cross a bunch of times. We see that we get 65 yellow smooths, 19 yellow wrinkleds, 9 green smooths, and 7 green wrinkleds. On the basis of this sample, should we reject the hypothesis of Mendelian inheritance? Okay, so the first thing that I want to do is figure out how many total plants I did the experiment on. So 65 plus 19 plus 9 plus 7. So I used 100 total plants. Now, what would I have expected under Mendelian inheritance? I would have expected that 9/16 times 100 of them would be yellow smooths. So that would have been 56.25 yellow smooth plants. These number expected don't have to be whole numbers. I would have expected that 3/16 of them be yellow wrinkled, or 3/16 times 100 would be the number that I'd have expected for yellow wrinkled. 3/16 is 0.1875 times 100 is 18.75. I'd have expected 3/16 to be green smooth, also 18.75. And I'd have expected 1/16 to be green wrinkled. Or 6.25. So now I have my listing of observed and expecteds. And I'll just come over to here and just borrow my spreadsheet from before. So my expected is 56.25. 18.75 for the next two, and then 6.25. And then my observed 65, 19, 9, and 7. And so I get about 6.52 for my chi-squared observed number. When I add up all the observed minus expected squared over expected, that's what I end up with. Now, should we reject the hypothesis? Oh, for that, I need a chi-squared critical. We'll use 5% as always. But my degrees of freedom here, well, I have 4 rows. 4 minus 1 are 3 degrees of freedom. So I'll go to my chi-square table. It's still a right tail test. So 5% in one tail in the right tail. But here I have 3 degrees of freedom. So my chi-squared number is 7.815. And again, remember, this is a right tail test. So if chi-squared observed is to the right of 7.815, then I would reject the null in favor of the alternative. I would conclude on the basis of this experiment that Mendelian inheritance is not the proper model for this inheritance pattern. But I say, since chi-squared observed of 6.52, is that bigger than chi-squared critical? It's not bigger than 7.815 or chi-squared critical. The observed value is not to the right of the critical value. It's not far enough into that right-hand tail. So since that's not true, we do not reject H naught. We conclude Mendelian inheritance is a reasonable model. So we would not reject the hypothesis of Mendelian inheritance. We would not say that it's unreasonable for Mendelian inheritance to be the way that this information is passed along. And we would not overturn the null. Okay. Any questions on any of this? So the ideas are all the same as in chapter 8, the hypothesis testing ideas. I think really the only real big thing here is this calculation can be a little bit cumbersome, right? If we're using Excel, that helps a lot. Even with the calculator, if the numbers aren't too bad, it's not bad. Like we did this one by hand. But something like this one down here, I think this would have been kind of a pain to do on the calculator by hand. But especially if we're using Excel, it goes pretty quickly, I think. And once we get chi-squared observed, as long as we remember that it's a right tail test, I think that's the big thing to remember. It's always going to be a right tail test. We calculate chi-squared observed, we get chi-squared critical. It's always a one tail test, so we know that we're always going to be in this side of the table, and usually we're going to be in this column because usually we're using the 5% level, and then it's just a question of how many degrees of freedom. That's the number of frequencies that we observed minus 1. That gets us our chi-squared critical number, and then we just ask, is chi-squared observed bigger than chi-squared critical? If it is, we reject the null, and we conclude that the actual distribution is not the null hypothesized distribution. Otherwise, we don't reject the null, and we proceed forward, presuming that the null is true. All right, any questions on any of this? So I think that's actually all I have to say for chi-square test for goodness of fit. When we come back next time, we're going to look at chi-square test for independence. It'll have a pretty similar feel to this one, actually, but there will just be like a little nuance that's a little bit different. And then we're also going to talk about ANOVA. And again, ANOVA, the analysis of variance, is a huge topic that could be talked about for quite a while, but we're just going to scratch the surface of it, do a couple of quick problems just so that you get the idea of what is this thing? What are we trying to do here? What's the goal? When we see the goal and we see the method, we might say that doesn't quite seem right. So we'll try to explain why the method we're using, looking at variances, helps us with our goal. Knowing something about the means, how does knowing something about the variances help us know something about the means? That seems kind of strange. And then we'll go through a couple examples for a simple ANOVA setup, and that will be the end of the course. So that's what we have coming on Monday. And again, this information, chi-square goodness of fit test, chi-square test for independence, and ANOVA, I also posted as a supplement already. So if you want to take the exam early, say over the weekend, you can watch those couple of videos and then be ready for the exam. All right. If there aren't any questions, then we will call it a day.